Okay, we're going to look at an optimization problem, achieve section 4.7, number 3. And I'm going to actually do this problem two different ways and show that one way is a little bit easier maybe than the other way in terms of at least the calculus and algebra part of it, so to speak. So let's take a look at it. We're going to find two positive real numbers such that they sum to 129. Of course, that means add, right? They add them up to, they add together to 129. And the product means multiplication, the product of the first and the square of the second. So I take the first number, square the second number, and multiply them together. And I want to know what two numbers that sum to 129 make that product a maximum. Okay, so how would you solve this problem on a test? Well, first thing is you need to assign variables to unknown quantities. What are the unknown quantities? The two positive real numbers and to the function you're trying to maximize, which is this product. Okay, so I'm just going to let x be my first number and y be my second number. Okay, so it's very easy to write this out. This helps a whole bunch. Clearly identify what your variables represent. Now, just don't start assuming, well, they're going to know, whoever's reading this is going to know what my variable x represents or what my variable t represents or what my variable l represents. Make sure you clearly define those. P is the product of the first and the square of the second, and that's what we're trying to maximize. So what would it be in terms of x and y? Product is what? The first x times the square of the second, y squared. So this is what I'm trying to maximize. It's a function of two variables. We need it to be a function of one variable. How do we get that function one variable? Well, the constraint now, the sum of the two numbers is 129, right? And so that means x plus y is 129. Well, our natural inclination when we're doing this is to get this as a function of x. We just like functions of x, right? We're just used to it. So you might want to say, let me solve for y by subtracting x from both sides. Notice in this case, because the two numbers were indeed positive real numbers, meaning they're greater than 0, that if y is equal to 129 minus x, x of course has to be greater than 0, right? It's positive, but it also has to be less than 129, because if we're 129 or more, y will be 0 or a negative number. Okay, so this is a restriction on x. It can only be in this interval. Okay, and that's important in this problem. Now, what we do then is we take this value of y and we plug it into the original function we're trying to maximize here, and I'll get it in terms of x only. Now, when I do that, since it's y squared, that 129 minus x gets squared, and I get this function. I can find the derivative and do all the work, and I'm going to show you how to do that, but it's more complicated. Okay, you could FOIL this out, right? Expand this special product, 129 minus x quantity squared, and then multiply by x. You would have a degree 3 polynomial. You'll have 3 terms, and then you can take the derivative of each term individually. I just went ahead and just used the product rule instead. So I did that function times this one. Well, the derivative of x is easy. It's 1. So I just have the 129 minus x squared. And then x times the derivative of this. Well, this is by the chain rule. I bring the 2 down in front, 129 minus x to the first power times the derivative of the inner function. And the derivative of the inner function is -1. So this is by the chain rule. Cleaning this up, I've got this first term, and it's going to be minus because this -1 will come up, -2x times 129 minus x. And then I can factor. Notice I've got a factor of 129 minus x here. I've got 2 of them and 1 here. So if I factor that out, that leaves me 1 factor of 129 minus x. And then minus what? Since I factored that 129 minus x here, I'm just left with 2x. And -x minus 2x, this stuff simplifies down to 129 minus 3x. Okay, so there's my derivative. So critical numbers is when the derivative is 0 or undefined. Well, it's never, this expression is never undefined for any value of x. It is 0 when x is 129, but remember our restriction, right? X had to be less than 129. So 129 is not a critical value, not a critical point. But 129 minus 3x is 0 when 3x is equal to 129, or when x is 129 thirds, which is equal to 43. So 43 is the only critical point of interest here. Now, do we just go ahead and say we're done? The two numbers are, well, 43 is X, and then I can find Y by plugging into here, and we're good to go. No, you have to show using calculus that indeed you have a maximum. Just because you have a critical point doesn't mean you have a maximum. The derivative is 0 at maximums, like a function that looks like this, right? The derivative at the top is 0, but you could also have a minimum, right? Right? It'd be pretty bad if you're doing a problem, later on in life as a uh, consultant or engineer or whatever, and you tell someone, yeah, we've got a maximum, and you actually give them a minimum. You're going to be fired pretty quick, probably. Okay, so make sure you indeed have a maximum. Or you can have a situation where it's like this, right, where the derivative is 0 right here, and you have neither a max nor a min. Okay, so make sure you have a maximum. How do we do that in how do we actually do that with first derivative test and a sign check? So this has to be done on the test. I'm going to ask you, make sure you prove you have a max or min. What's that mean? Do a sign check. If it's a closed interval, you can just check, remember, the value of the endpoints and check the value of the function at any critical points and just find the maximum from that list. But since this is an open interval, right, we can't include the endpoints. We have to do a sign check on the derivative. 43, we know the derivative is 0. If I choose something between 0 and 43, like 1, if I go back to my derivative right here, if I plug in 1, 129 minus 1 is 128. 129 minus 3 is 126. Well, positive times positive is positive. If I choose something bigger than 43, like 44, this will be positive. This will be negative. The product is negative. Okay. This is good, though, because I have a sign change in my derivative from positive to negative, which means I have a maximum, right, from increasing to decreasing. So we're definitely, have a situation, something like that. And so now I know X is 43. I can plug back in. Remember, we solved for Y here, 129 minus what X was 43 is 86. So these are the two numbers, 43 and 86. Now, I said I would do this two ways. So I want to just go back, it wasn't that bad to do this work, but it actually turns out to be a little bit easier if instead of making this product here a function of X by solving for Y here, we make it a function of Y by solving for X. If I solve for X, it's the same thing, right? 129 minus Y, and that's what I've done here. Okay, so what if I instead do this? Now the value of Y, like we had the value of X, has to be between 0 and 129 for the same reasons. And if I now plug in and replace X with 129 minus Y, I have 129 minus Y times Y squared, and I can just distribute this Y squared through, and I get this. Well, this is easy to take the derivative of. I don't have to use a product rule at all. Bring the 2 down, I get 258Y. Bring the 3 down, 3Y squared, right? Factor out a 3Y, and we've got this. And clearly this is going to be 0 when Y is 86. We don't include 0 here because, again, Y has to be greater than 0. That's the only critical point. If we do a sign check on this derivative here, right, we get is positive for values less than 86, negative for values greater than 86. So we indeed have a maximum. And again, I can now plug back in the value of X is 129 minus Y, which gives me 43. I get the same two numbers, of course. So either way works, just one, maybe this one a little bit simpler, but sometimes, it's okay. Sometimes if you try it one way, it's getting really hard. Sometimes you can create a function that's really hard to find the derivative of. You might want to try and see, hey, can I solve for a different variable here to make my function that I'm dealing with easier to work with. Okay, I hope this is helpful for you, and let me know if you have any questions about it.